In the network layer, we've gone through IP. If we draw our stack of a computer, in the network layer we have IP. Underneath we have different data link and physical layer protocols. Then above we have transport, application. In the internet, our hosts use IP at the network layer. We're going to now look at the transport protocols, and it turns out there are multiple transport protocols. The general role of a transport protocol is to allow us to send data between application processes on our hosts. You know the structure of software. We write a piece of software, it runs as separate or as a process on your computer. So to allow a process on my laptop to communicate with a software process on another computer to send data is the general role of a transport protocol. IP is more about getting data between devices, between computers. So if we have two computers, some source host, and some destination host, two computers somewhere in the internet, they are connected by some routers. Maybe many routers, and in between routers may be different devices, so the different subnets here. The routers use the internet protocol. We know the basics of the internet protocol is the source creates a datagram, sends it to the first router, to the next router, and eventually it gets to the destination. We hope. IP makes no attempt to make sure it gets to the destination. That is no reliability. Transport protocols at the next layer up are about allowing applications on the hosts to communicate with each other. And we see that the routers don't have any role in the transport protocol. Here's the transport layer. The transport protocols are implemented just at the source host and the destination host. From the router's perspective, it doesn't know what transport protocol or care what transport protocol may be used. They don't have any role in the protocol. It's just that the hosts. So we often say that transport protocols are for end-to-end communications or host-to-host communications. The intermediate devices have no part in the protocol. Just here. There are different transport protocols available. TCP, UDP, SCTP, DCCP are some of the standardized protocols. There are some older ones. There are some that are very specific, used for very special networks or very domain-specific networks. TCP and UDP are the ones that have been around the longest. These other two are quite new in terms of the, maybe in the last 10 years or so. TCP and UDP, I think TCP around 1970, so that's 40 years old. And TCP and UDP are the main transport protocols. And in fact, of those two, TCP is the most commonly used one. We're going to spend most of our time on TCP. TCP does those things that IP does not, and that are useful for applications. It sets up a connection. IP does not set up a connection. So before we send data, we tell the receiver, we're about to send data. Do you want to receive it? Are you prepared to receive it? We set up a connection. We provide reliability by having error control in TCP. If we send some data, and if it doesn't get to the destination, we will send it again. That's the basics of error control in TCP. IP does not do that. It's needed by most applications, because if something goes wrong in the internet and someone's sending you an email, then it's of no use to you if half of the email message is missing. Okay? You need to receive the full email. TCP provides flow control and congestion control. We'll explain later why and how they work, well, why they are needed, what they are and why they are needed when we look at TCP in detail. UDP, the other one that's been around the longest, is almost the same as IP in that it doesn't provide connections, it's connectionless. It doesn't provide error control or flow control or congestion control. The same as IP. You just create a packet, send it, hope it gets to the destination. We will not cover UDP in much because it's so simple and so similar to IP. Amongst all these different transport protocols, there are some common things, especially addressing. So let's spend some time on addresses. Now, we use IP addresses to identify computers in the internet. More specifically, to identify interfaces. My computer may have multiple IP addresses, one for each interface. But generally we think, if I know the IP address of a computer, then I can find it in the internet. I can send something to it. So we think IP addresses identify computers in the internet. But on each computer, there may be multiple applications. On my laptop, I'm running a web browser, an email client, an instant messaging client, and a voice over IP client. 4 different internet applications. Someone can send data to my computer because if they know my IP address, but we need another address to indicate which of those 4 applications should receive that data. Okay? And that address is called a port number. So we use port numbers to identify applications on computers. We use IP addresses to identify computers in the internet. All of the transport protocols make use of port numbers, so we'll go through that first. Specifically, a process on your computer, a software process, will have a port number assigned to it if it wants to communicate. So we'll see when I start my Firefox web browser, it may have multiple port numbers because it may communicate via multiple connections at once. We'll see some examples. So let's go through port numbers, or generally addressing. Those applications we listed at the start, web browsing, email, instant messaging, voice over IP, video, BitTorrent, all of them follow the same model of how they communicate, in that there's normally a piece of software that acts as the client and another piece of software that acts as the server. So this client-server model. What happens is that it's the client that initiates the communications. Someone needs to start the communications as the client. The server software normally is running on some computer, but it's doing nothing. It's just waiting for a client to initiate communications. So a client initiates communications. How? By sending a message to the server. So assuming the server's on one computer, a piece of software is running there, waiting for a client to send it something, then I start my client application on another computer. That client application sends a message to the server, and now the server may respond, and then they start communicating, sending data. The question that arises is, how does that client know the address, or how does it know where to send the message to the server? It needs to know the address of the server, in particular the IP address. So if I want to send a message from my web browser to the web server at Facebook, I need to know the IP address of that web server at Facebook. How do I know it? How do I know? Does anyone know the IP address of the web server at Facebook? Has anyone used Facebook? But you don't know the IP address. So how does your web browser contact the domain name? And again, in the assignment, I think you see this, that you open your browser and normally in a browser you type in a domain name. There's another protocol, DNS, that goes to work in the background when I press enter, and what it does is for the Facebook server it finds the corresponding IP address. So when I press enter, DNS works, and DNS goes and finds the IP address of the Facebook server. The domain name's just for me as a human. My computer uses the IP address to send the packet. Okay? So we know the IP address of the server. But on that server there may be multiple applications. Maybe there's a web... So on that computer, on the computer with the IP address for the Facebook website, there may be multiple applications. A web server application, an email application, and others. We use a port number to identify which of those applications our data is destined to. For example, here's some computer. Let's give it an IP address. What is the IP address of Facebook? Anyone know? We can look it up. .13.79.20. In reality, it's more complex in that Facebook probably has many servers distributed across the world. So it makes it faster for us to access. But that's one of them. So whenever I type in that domain name, my computer actually finds the corresponding IP address like it's done here. So that's the IP address of the computer. My computer has an IP address. Let's just give it 1.2.3.4. So now that I know the destination IP address, I can send something to this computer using IP. But it may have a web server application running on it, just a piece of software, an email server application, and maybe some other voice over IP application running on that same computer. So we use a port number to indicate which of those three applications my data should go to. I can get the data to this computer because I now know its IP address, but more specifically I want to get the data to one of the three applications on this computer. So the applications, or precisely application processes, have port numbers assigned to them. Port numbers are 16-bit numbers, and they have, numbers in different ranges have different meanings or different uses. We'll go through that a bit later. What's the port number of the web server? Anyone remember? 80. Many servers which are commonly in use in the internet have a fixed or well-known port number. The port number of the web server is normally 80. It can be different, but the default value is 80. Of an email server is 25. Voice over IP, it varies. Let's give it a number, say 5001. So we can think the servers have some port number assigned to them. And we use that port number when I send my data. I set the destination IP address to 31.13.79.20, so it reaches this computer, and I set the destination port number to be 80. So on this computer, it reaches the web server software, not the email software, not the voice over IP software. So we use port numbers to identify the application. The other thing that we have is we may have multiple different transport protocols in use. So we have, for example, TCP, UDP, and others. Most applications will use just one, some use two. Usually it's fixed. We also, when we send our data, we tell this computer at the destination, okay, the destination address is 31.13.79.20. IP receives it. IP needs to know which transport protocol do I send the data to. Do I send it to TCP? Do I send it to UDP or someone else? We use a protocol number to indicate the transport protocol used. We saw this in the IP header. The IP header has this value in it. It says, if we're using transport protocol TCP, the protocol number will be 6. If we're using UDP, 17, and there are other numbers for other protocols. So in fact, we have 3 addresses now. In general, IP addresses to identify computers in the internet, protocol numbers to identify transport protocols, port numbers to identify applications or application processes. The set of protocol numbers and port numbers are defined and managed by some organisation, IANA. And on these websites you can see the set of values that have already been registered or in use. Let's have a look. Protocol numbers. So this organisation maintains a list of the protocol numbers. Number 6 is assigned to TCP. 17 UDP. 1 ICMP, and there are others. Some are old protocols, some are current ones still in use. And there are many there. These are the transport protocol numbers. And similar, the same organisation maintains a list of port numbers. These are 16-bit values. And there are 3 sets of port numbers. They're on the slide. Well-known port numbers, registered. Are they registered or? Yeah, registered port numbers. Yep. And dynamic, let's call them dynamic. So with a 16-bit value, we have about 65,000 possible port numbers. 0 up to 65535, and those port numbers are divided into 3 groups. The well-known port numbers, and this is on your slide I think, going from 0 up to 1023, registered 1024 up to, and it's shown also here, 49151, and the rest up to 65,000. And over time, this organisation, IANA, maintains a list of both the well-known and the registered port numbers. They are mainly used for servers. And it's not always the case. The dynamic mainly used for clients. The well-known port numbers are port numbers for protocols that have been around a long time, for servers that have been in use for a long time in the internet. And if we scroll down, we start to see them. They are listed here. This is the short name. This is the port number, the transport protocol, and the longer name. Let's see if we can see one that we can recognise first. Anyone? What do you recognise on that one? What application or port number do you recognise? What application? Where? On this screen. Start simple. SSH, when you connect it into the IT server to transfer files, to change your password at the start of the semester, you used a protocol called SSH that it connects from your computer. You may have used, what is it, PuTTY on Windows or SSH on the command line in Linux or Mac to connect from your computer into this remote, the IT server. The protocol uses SSH, allows you to log in to another computer. The port number used by SSH, the server, is 22. Okay? So when you connected to the SSH server on this computer, the port number the server was using was 22. FTP, some of you may have used FTP to transfer files. That uses, in fact, two port numbers, 20 and 21. Email servers use SMTP to transfer email. Email servers use port number 25. And many others there. World Wide Web, web servers, HTTP or www is the short name, port number 80 by default. You start a web server on your computer, then by default it will listen, it will wait to receive data on port number 80. So when someone tries to contact your web server, they guess or they assume that you're using port number 80. If you change the port number of your web server to 81, for example, then for someone to contact your web server, they need to know it's 81. Because normally a web browser will assume it's port 80 that a web server uses. And there are others. So these are well-known port numbers. The registered ones are similar, except they've been added perhaps more recently. And let's say you develop your own game. Okay, so you make the game client, it's a multiplayer game. People download the software, and your game involves communicating back to a game server. So you've developed your own protocol to talk between the client and the game server. So what you may do is find a free or an unused port number. We have to go past 1023. Find an unused port number. Most of these are in use. If we scroll down even further, somewhere up to 49,000, and your game server would use that port number. Any free ones there? Not many. For example, well, let's find where there's a much more free space. Okay, now we're getting close. Here, there are some unassigned port numbers, for example, not yet assigned, from 22952 up to 22999. So your server, for example, you choose a port number for your server to use, 22953. You register that port number with this organisation, they add it to this list, and now anyone who's using your game client will connect to that port number, and that becomes a registered port number. The idea of registering is that someone else who creates a different application shouldn't use the same port number. Okay? So someone else comes along, they shouldn't use the same one that's already in use. They can, but they should not. So the registered and well-known port numbers mainly used for servers. The remaining port numbers are used by the clients. They are not listed here. They are chosen by your operating system when the client starts. When your web browser starts, the operating system gives it a port number in the dynamic range and gives it a value that's not currently in use by other applications. So So what happens is normally servers use well-known port numbers. Servers listen in or wait to receive data from that well-known port number. A client, when it starts, the operating system, say on my web browser, assigns a port number that's not currently in use by my computer. And when I send data, there are 5 addresses used. There's the destination IP address, so we know which computer needs to receive it on the internet. There's the protocol number, so we know at the receiver which transport protocol is used. That's 2. There's a destination port number, so we know which application on this computer receives it. And the other 2 addresses are destination IP, destination port, protocol number, and there are 2 more addresses needed. What are they? Normally, our application, when we receive the data at the server, it wants to send something back. So the other 2 addresses which are important are the source addresses. The source IP and the source port number. When we talk about communications between applications on the internet, those 5 addresses usually uniquely identify a set of communications. So when we send an IP datagram, we indicate the destination address and the source address. Why the source address? So the one who receives it can respond. They know who to respond to. Same with the port number. When my browser sends to the web server destination port number 80, I also indicate the source port number so that the web server can send back a response that goes to that browser or that instance of the browser. Let's see an example. On my computer, I can use a program called Netstat to show me some information about my internet application connections. I want to look just at the protocol using IP, the internet protocol, INET in this case. This program sometimes will normally list the domain name. I want to just list the IP addresses, the numeric form, not the human-friendly form. What it shows is of the recent communications by my computer, who have been communicating. And there's just one in this case. It shows, this is my address, my IP address, 10.10.99.251, my computer, has been communicating with some foreign computer, 91.189.89.134. And communicating with the web server on that computer, port 80. And the port number used by the application on my computer was 60730. A port number assigned to my web browser, most likely, or at least a client on my computer. So that's just one example of communications. The protocol used was TCP. These are just some indicators of the queue length, the packets that are queued to be received or to be sent. We will see later that TCP, we open a connection and then send some data and then close a connection. This state indicates what step we're in. Here we're waiting to close the connection. Maybe we've finished sending data, we're going to close the connection soon. If I keep looking, sometime later we may see this line disappear if the connection closes. Now let's access some website. Let's access the IT server. Okay, I just accessed the IT server. And let's look again. Bad example. because my browser didn't have to access. Let's access a different page. It's in my cache. Sorry. Let's click on a link. Still on the IT server. Just clicked on a link. Let's show again. Now we see some useful information. Let's go through them. Which number?
The one that you just explained. Can I touch it? 6073.
Okay, the one down the bottom is the one that was there before. It's from, and I think my computer has been connecting to the Ubuntu website, the Ubuntu server recently to do some updates. So that's what the one at the bottom is. That was there when we looked earlier. But there are also these 7 new lines at the top. They are the connections from my computer to the IT server. When I access the web page, I know the IT server's IP address. I can remember it. It's this one. 72. That's the IP address of the IT server. It's somewhere, it's in fact downstairs on the 3rd floor. So the first line shows that my computer, 251, an application using port number 58267 contacted or communicated with this other foreign computer, which is the IT server, and the application on that foreign computer was a web server. We know that by the port number 80. And it used Transport Protocol TCP. It established a connection in that case. The state of the connection is that it was established. And we look at the subsequent lines and we see that still my computer, still the IT server, still the IT web server, but different port numbers on my computer. 6 or 7 different cases there. What happened is that my web browser, what I did is access this website. My web browser opened one connection to download the web page, then realized there were many images in this web page and had separate connections in parallel to download those images. That's what most likely happened. So my web browser actually had multiple connections. That is, we see multiple port numbers in use, all by my web browser in this case. Where did the port number 58267 come from? My operating system gave it to my web browser. So Firefox was assigned this port number when it set up a connection to send data. And when Firefox wanted to make another connection to download the image, the operating system gave it another port number. And for each time my web browser wanted to download an image, it got a different port number then. They're gone. My web browser established connection to the server, downloaded the data, and then after downloading the data, closed those connections. Now I look at the connections which are open, and none of those initial 6 ones are existing anymore. They've gone. With TCP, we open a connection, transfer data, close a connection. This software only shows the ones that have been opened. Okay? So I've finished communicating with the IT server. Time wait is the state of TCP. Basically what happens is that TCP opens a connection and then it's called established. Transfer the data. Once we've finished transferring the data, we start to close it. But we go through different steps. We try to close it, but we give the receiver some time to wait before they close the connection. So there's some sub-states of time wait and close wait here. It's how TCP manages the connection. One more example. Let's connect to Google using HTTPS. what are we going to see? Not on the web browser. I just connected to the Google website, but instead of using HTTP, I used HTTPS, which is a way to connect to a secure web server. We see the connections from my computer, my web browser, to the Google server. In fact, the Google server is distributed across different computers. We see different IP addresses here. Note the port number, 443. When you use HTTPS, a different port number is used by the secure web server than a normal web server. A normal web server uses port 80 here. A secure web server uses a different port number, 443. Okay? So we can see that connection being established. Any questions about port numbers or protocol numbers? They're used on multiple transport protocols. This captures in a bit more detail what I've tried to show here. The fact that on a source or destination host, we may have multiple transport protocols, and the protocol number is used to identify which one is in use. And we may have multiple different applications, and a port number is used to identify which application we send our data to. Okay. If I send data to this computer, if the destination is port 80, it will go to the web server. If the destination is 1863, it will go to the instant messaging client. If it's 5001, it will go to the voice client. That is, each application will have a different port number assigned to it and used to identify which one will receive the data. So 5 addresses are important. Let's just list them. The 5 addresses normally involved with our internet communications: source IP address, destination IP address, protocol number, source port number, and destination port number. In brief, these identify computers in the internet, more specifically interfaces of computers in the internet. Protocol number identifies the transport protocol in use. And the port numbers identify applications or application processes. The first 3, the IP address and the protocol numbers, are contained in the IP header. The port numbers are stored in the transport protocol header. E.g., the TCP header or the UDP header. So when we send some packet across the internet, in the IP header we should see these 3 values, and in the, say, the TCP header we'll see the 2 port numbers. And you probably saw them, or you noticed some of them when you looked at the Wireshark capture in your assignment. You would have seen some of those values. So make sure you understand what the different addresses identify. Some identify computers, some identify transport protocols, and some identify applications. Any questions on the general addressing? Everything okay? Easy so far? The next part's even easier. UDP is one example transport protocol, but it basically does nothing. Compared to IP, it doesn't do any more. All we do with UDP is that we take some data from the application, we attach the UDP header. UDP header looks like this. Four fields: source port, destination port, total length of the segment, which is the data plus the header, and some checksum so that the receiver can detect if there's any errors inside. We take our data from the application, attach these 4 field values, so attach the UDP header, and then send it via IP. Application data, UDP attaches a header, sends to IP. IP delivers across the internet. The receiver, if they receive it, removes the UDP header, sends the data to the application. Which application? Whichever the destination port number tells it to. In the same as IP, UDP does not provide reliability. There's no retransmissions. If we send our UDP segment and something goes wrong in this subnet, it won't arrive at the destination. The source won't try and fix that. Okay? It doesn't provide reliability. As a result, segments may be lost. They may arrive at the destination in the wrong order. We may even, in some cases, receive duplicates. I send one, the receiver receives 2 copies of that. It's possible. UDP is very simple. If you look at the description of it, it's about 4 pages long. We'll see TCP, the standard that describes it, is more than 100 or hundreds of pages in length. It's more complex. Why would you use UDP? Well, if your application doesn't need the features of TCP, or if it needs to be very simple. If you're creating an application that allows you to communicate with some embedded device, some small router, some projector. You want to send an IP packet to the projector and you want to make the source code or the code, the memory usage to be very small, then maybe use UDP, because to implement UDP is much simpler. You don't need so much memory space. So in small devices, maybe UDP may be used, where we need simplicity. UDP does not provide reliability, so it's only really suitable for applications that don't need reliability. That includes many multimedia applications. Making a voice call or a video call, FaceTime for example. Making a call over the internet, we don't necessarily need to receive all of the data. If you're streaming a video, and some packet containing that video doesn't arrive at your computer, you'll still see the video. Maybe just some pixels don't show up correctly for a fraction of a second, but if you keep receiving the rest of the data, you'll still see the video and it'll be okay. So with some voice and video applications, even if we lose some data, the application still works. In that case, using UDP may be suitable. Because it's simple, there are very few overheads, no retransmissions, and works well if we want to have very low delay in communications. Again, voice and video apps. So UDP is used in some special cases. But if we want reliability, normally UDP is not a good choice. The choice is TCP. The Transmission Control Protocol. UDP, the User Datagram Protocol. Almost all of the applications you mentioned at the start of this lecture use TCP because they all need reliability. Maybe the exceptions are the voice over IP and the video over IP applications. Most applications we use on a daily basis make use of TCP. What does TCP do? These are the features of TCP. Let's not go in order. Let's start with the simpler things. It sets up a connection before we send data. So when I want to transmit data to my server, I first set up a connection. We agree upon some parameters. We make sure that the server is prepared to receive the data. And once the connection setup has been successful, then we transfer data. So we say it's a connection-oriented data transfer. We set up a connection, then send data. When we're finished, we close that connection. And that's what you saw in this Netstat program. This state was the state of the connection. Was the connection established, or was it being prepared to be closed? And there may be some other states, although they're hard to see in this case. Set up a connection, send the data, close the connection. Once we set up the connection with TCP, we consider a full duplex connection. It means if my source host initiates communications to a server, and then we set up the connection, after it's set up, I can send data to the server and the server can send data to me. Okay, that's all it means. Full duplex, we can send in both ways once it's set up. Importantly, we have reliability in TCP, or error control. If I send a TCP segment and it doesn't get to the destination, eventually I may retransmit that segment and keep trying until it does get to the destination. So we have sending data segments, sending back ACKs, retransmitting where necessary. So we have reliability. Flow control. What is flow control? We've studied it before, or maybe slightly after the midterm. Remember stop and wait flow control and sliding window? The idea, make sure the sender doesn't send too fast such that it overflows the receiver. That's the concept of flow control. In our case, let's say our server is a slow computer, my laptop, maybe that's the server. And the sender is a fast computer. And the network is very fast. So what happens? We send packets as fast as possible. They start arriving at the receiver. The receiver puts them into some buffer, but it's slow to process them. The CPU is slow, it's taking time. More packets are arriving and arriving, and they're waiting and waiting. Eventually the buffer at the receiver will fill up and will be full, and we'll have to start dropping packets. Okay? We don't want that to happen. Flow control is about making sure the sender doesn't send too fast such that it overflows the receiver. And TCP implements some flow control mechanisms so that the receiver tells the sender how much it's allowed to send so that it's not overflowed. Congestion control is similar, except it's about not overflowing the routers in the internet. Flow control is about controlling the sender so that we don't overflow the receiver. Congestion control is about controlling the sender so that we don't overflow the routers between the sender and receiver. If this router is busy because it's receiving packets from many other computers, and we send too much, we start to get congestion in the internet. Like you get congestion at an intersection in the road. Many cars arrive, it's slow going out because one lane is closed, the queues build up. If it's slow sending out here and many arriving, then eventually packets will be dropped by this router, and that causes a problem for our sender. So TCP implements some algorithms so that the sender will control the speed at which it sends to try to avoid congestion, avoid overflowing the routers. They are the main features of TCP. Set up a connection, error control, flow control, congestion control. And each of them are quite complex. In this course, we will not explain how they all work. We will only get a chance to look at the very basics of error control. We will not explain how flow control works. You know the basics of flow control, stop and wait, sliding window. TCP uses sliding window. We will not explain congestion control, and we will not explain the details of setting up a connection, just a simple case. Because it's very complex, it takes several lectures to cover those features. The other part is, and we'll see that I think next week, is that TCP is stream oriented. Let's explain that next week when we've got an example. Let's go instead and look at the segment and how to set up a connection. There's one type of TCP segment, and the header is shown here, where we normally have 20 bytes. We can have some optional fields in the header. We don't have to. If we include some options, then it's important that we have a header length field here to indicate how many options are included. And then we have data. So a TCP segment has the 20 byte header, optionally some other fields to increase the size of the header, and then the data. In the header, we include the source and destination ports, so we can identify the applications. We have a sequence number. Because we have error and flow control and congestion control, we keep track of the data that we're sending. We send one segment, and then another segment, and another segment. We use a sequence number to keep track of them, the ordering of them. Similar, we send data, and the receiver sends back an ACK. And the way we use acknowledgements is that we have an acknowledgement number. I send data with sequence number 1, then the acknowledgement coming back says, thank you for that data, I now expect 2. That would be the acknowledgement number 2. In fact, it's a bit more complex than that, which we'll see later. Header length, reserved, is reserved for future use. Advertised window is used for flow control. Urgent pointer is used to give some priority to some of the data. Checksum is used for the receiver to detect if there are any errors in the segment. And some flags, which we'll explain with a more detailed example. So there are the segments, the header fields listed. Let's look at the flags. What's a flag? When we talk about a protocol. Offset, simpler. When we talk about protocol headers and protocols and flags, a flag usually means a 1-bit value. It's either the flag is on or it's off. So if that flag has the value binary 1, it means that feature is on, and if it's 0, it means it's off. Okay? So when you see flags, that's the idea. A flag, in TCP, there are multiple different flags. They are listed here. They mean when they are on, that is when they have value binary 1, it means that feature is on, or that, that feature in the segment is on. Let's look at some of those features. The first three we won't look at. They are used for special cases, congestion control and priority of data. ACK. There's only one type of TCP segment. We have a header, maybe we have some data. We send from A to B a TCP segment. Inside the TCP header, there are some flags, so some bits to indicate different features. One of those is the ACK flag. If the ACK flag has the value 0, it means this segment is not an acknowledgement. If it has the value 1, then it means this segment includes an acknowledgement. It includes an ACK. Okay. So what we may do is send some data to B. The ACK flag is 0. It's possible B sends back to A TCP segment with no data, and the ACK flag is 1. So we would call this a data segment, and this would be an acknowledgement segment. The header structure is the same, it's just the flag indicates the meaning of that segment. Here it's not an ACK, this is an ACK. Importantly, we can use multiple flags at the same time. That is, we can set different flags to be on. And a common example we'll see is this SYN flag. Let's try one more case. We will see the process of setting up a connection shortly. What it involves is sending some special synchronize messages to synchronize sequence numbers. A sends a TCP segment to B. It sets the SYN flag to be on. B sends back a response. And it also sets the SYN flag to be on, to synchronize. And it also sets the ACK flag to be on. Meaning this segment has two meanings. The purpose is it's used to synchronize values, and it's also used to acknowledge previous segments. So we can use multiple flags at the same time. In my diagrams, if I don't specify a value, I mean it's off. So here, ACK is on, all the others are off, that is 0. In this segment, SYN and ACK are on, all the others are off, that is binary 0. So we can combine the flags in our segments. We have flags to indicate whether this is an acknowledgement or not, to reset a connection when we want to close it, something's gone wrong. To synchronize is to use to open a connection, to start the connection, and fin to finish a connection. When everything's okay and we want to finish, we send a fin message. Reset is when something goes wrong and we want to close. We reset the connection. To finish today, we'll look at how we set up a connection, just the simple process of setting up a connection. And we'll see those flags in use and also the sequence numbers. In TCP, we use sequence numbers to keep track of the data that we send. First piece of data, sequence number 1. Next piece, a larger sequence number, 2. It's not that simple. But when we start our connection, instead of starting at sequence number 1, the computer can choose where to start. It may choose an initial sequence number. So when A connects to B, A chooses an initial sequence number, and B also chooses chooses an initial sequence number. And the values chosen by A and B are independent. They're not related with each other. So to set up a connection between A and B, A chooses an initial sequence number, tells B. B chooses its initial sequence number and tells A. And once they know each other's, then they can start sending data. So that's one role of setting up a connection, to tell each other or to synchronize the initial sequence numbers. Let's see how that works. It's shown here. I'll draw on the board a bit more detailed example. Let's say my web browser wants to create a connection to a web server. Then from the perspective of TCP, before we can send data to the web server, I need to set up a connection. And the normal connection setup is called a three-way handshake. And the steps are shown here. It's an exchange of 3 messages. The handshake meaning we're making some agreement between the sender and receiver. And in this case, it's an agreement on the initial sequence numbers. What happens is, in my case, computer A wants to set up a connection to B, the browser to the server. TCP at computer A chooses an initial sequence number. And the initial sequence number is chosen. It doesn't have to be 0. In practice, it's normally a number that's larger than what was used in a previous connection. But I've just chosen here some random number, 316. It's a 32-bit number. It's chosen by A. That's the first sequence number it wants to start with in the connection. And it creates a TCP segment and sends it to B. And that's what I'm drawing up here. Inside, so here's our TCP segment. There's no data. This is a connection setup. So it's a TCP segment with header only. The fields in this header include a source port, and the source port is the port number assigned to the web browser in this case. Let's choose some random number, 50111. Destination port, and it's the port number used by the web server, which should be port number 80. This is a special type of TCP segment. It's used to synchronize initial sequence numbers, so we call it a SYN segment. In particular, we set the SYN flag. Like over in this case, the SYN flag is set to 1. And importantly, we include a sequence number. And in this first segment, the sequence number is the value chosen by A, 316. That's just 4 values of the header. This is the entire header here. I've shown just the source port, destination port, one of the flags, assuming all other flags are 0 or off, and the sequence number. The other fields have values, but we don't care what they are in this example. We send that to B, assuming everything's okay. B receives it, and B chooses its own initial sequence number. So we'll continue our diagram. After receiving that first message, B accepts and is going to respond. The response from B is going to do two things. B is going to choose its own initial sequence number and tell A, the same way as A told B. Also, B is going to acknowledge the one it just received. So B sends one TCP segment. The headers, source port, value. What's the source port? 80. Destination?
50,000.
The first segment came from port 50111 going to port 80. Therefore, the response is the opposite. This, in this case, B chooses an initial sequence number. Let's say 1049. It's independent of the value that A chose. And B sets the SYN flag to be true, to be on, and sets the sequence number to be the value it chose, 1049. So all that's happening here is that A chooses an initial value, tells B, B chooses an initial value and tells A. So they know what each other have chose. The ISN is the initial sequence number. When we send our data, we will give sequence numbers to each segment. Which value do we start at? We don't have to start at 0. And there are some advantages of not always starting at 0. So in fact, we allow the computer to choose which value to start at. So B wants to start at 1049 when it sends data, and A wants to start at 316 when A sends data. They're independent because they may send data in both directions. They will use different sequence numbers. It could have been 0, but in practice, usually it's a number that wasn't used recently. Now, the other thing that this segment does is it acknowledges the segment that was just received. We just received a SYN message, so we send back an ACK. So what we do in the same segment here is set the ACK flag to be on and set the ACK number to be what? B, in the first step, B received a message including sequence number 316. To acknowledge, B sends back an ACK saying the next number I expect is 317. The next value expected. That's how our acknowledgement numbers normally work. So this is the first part. B received this one with sequence number 316. This is A telling B, I want to start with 316. Now B responds and says, okay, I accept that. So therefore the next one I expect should be 317. Okay. And now and later, if we send data, A should start with 317. Almost finished. So this second segment has two purposes. The first purpose is for B to tell A about its chosen initial sequence number. The second purpose is for B to tell A that it accepts and acknowledges the ISN chosen by A by sending back ACK number, this is 317. The last step is to send the final ACK. Source 50111, destination 80 still. ACK flag is on. ACK number 1050. Those three follow each other. That is, it's three messages there. A to B, B to A, and then finally A to B again. Our three-way handshake. Purpose, and it's summarised here. The purpose is for A to tell, well, the purpose is to synchronise sequence numbers. A chooses the value it wants to start at, tells B, B acknowledges that, and also B chooses its value and tells A. And then finally A acknowledges B's value. And that's the normal way to set up a TCP connection. After that, they can start sending data. Starting with the values, in our case, 317 and 1050. That is, the first data that A sends to B will have sequence number 317, and that B sends to A would be 1050. They use independent sequence numbers in each direction. Questions?